What is, remember types of bonds? Okay, we got covalent. We got, okay, chemical bonds are like the big umbrella. And then after the chemical bonds, we have types. We have covalent. What you got? Ionic. That's probably all you learned. What? Carbon. Okay, so carbon is going to form a covalent bond. Yes. And hydrogen bonds. Okay, good. We're going to talk about 4 bonds real quick. Not too much, and we're going to work our way through the notes and do some activities as we go. I'm not giving you a whole lot of information on bonds, but a little bit. So, let me get to the right spot. Here. This. Guys, I'm having to record my lessons, so if it goes crazy in here, sorry. All right, so we have these pictures. Y'all see them? All right, and if you look at this picture, what do you notice about these atoms? How are they connected? What? Okay, by 4 little circles, right? Y'all see that? These little circles are your electrons. So each of these little circles are your electrons. So could you say that this atom and this atom are sharing electrons? You see how they're sharing? So covalent, so think of a co-captain of something. If you're co-captains, does that mean that one person does everything and the other one doesn't do anything? No, you share responsibilities, right? So covalent bonds is where we share electrons, but we're going to say we share them equally. And this E negative represents electrons, because electrons are negative. So they share electrons equally. What do you notice is happening in this picture? Are they sharing them? No. Look at the arrow. One is being given to another, right? They're being transferred. Well, if an electron is negative, right? We said it's negative. So if this one gives away a negative, it would become what charge? Positive. So if you lose a negative attitude, you have a positive attitude. Well, if you gain a negative, what happens? You get a what? Negative charge. Right? So if you have a friend that's hanging out with you and they're negative all the time, you start to become negative. So when an atom gives away an electron, it loses a negative, so it becomes positive. Another atom gets the electron, and it becomes negative. So now we have a positively charged atom and a negatively charged atom, and opposites do what? Attract. So if a positive and a negative atom are sticking together, but they're just attracted. Are they sharing? No. So in an ionic bond, electrons are transferred. Creating charges. We call these ions. We'll say opposites attract. That's not official chemistry term, so I'm putting it in quotes for you. So after when you have him and you're like, yeah, opposites attract, you might be like, there's more chemical terms for that. But right now, we're going to say opposites attract, okay? This one down here is called a polar covalent bond. So compare this one to that one and see what you think. Similarities, differences. Just look at the actual molecule. Look at the shape of this with 3 atoms and the shape of that with 3 atoms. All these atoms are going, are they crooked? Are they in a straight line? They're what? Straight line. Well, are these in a straight line? We have one here, and one there. So it's bent. Will you agree with that statement? Okay, so a polar covalent bond, it makes things bent. Do you see any positives or negatives on this one? Do you see any positives or negatives? What about on here? Yeah, we have positives and we have negatives, right? So it has charged ends. But what do you call the ends? The top and the bottom of a globe? The poles, right? Yeah, poles. The North Pole and the South Pole, right? So if we have a positive and a negative, could we call them poles? So we call this a polar covalent bond because it has a negative end and a positive end. But you see these electrons? This hydrogen is still attached to those electrons, and the oxygen is attached to the electrons, so they are sharing them. But who has most control of them? The what? Well, who has most? These are the electrons right here. Who has most control of those electrons? The hydrogen or the oxygen? Oxygen. The oxygen, it has a higher electronegativity, but it's greedy. Okay. So since it's greedy, it's trying to keep them, but hydrogen's holding on for dear life. But this is when electrons are shared unequally. So do you see the difference between this polar covalent and this covalent? Here, they're being shared equally, equidistant from both atoms. But here, oxygen's super greedy, and so it's going to try and steal the electrons, but hydrogen's going to hold on for dear life. All right, it's kind of like if you have a sibling and they're a little bit older and you both want to play the same toy when you're little, and that older sibling is a little bit stronger, and so they're pulling it and they're keeping it real close to them, but you are holding on for dear life. You're not going to give up, right? You might have your fingertips on that toy because you want it. That's hydrogen. All right, it's hanging on, but oxygen is getting most control of it. So we have covalent, they're shared equally. Ionic, we transfer, and then the opposites attract. Then we have polar covalent, where they're shared but unequally, making a bent molecule with charged ends or poles. Then we have what is called hydrogen bonding. See how it's a dotted line? It's more of an attraction than a bond. So what is stronger? You having an attraction to somebody, or you actually having a relationship with somebody? A relationship, right? So an attraction is not very strong. All right, so this is a very weak bond. And notice it's not just one atom to another, it's this molecule to this molecule. Where is this forming? What do you notice about this nitrogen? It has a what charge? A negative. And this hydrogen has a positive. So it's that weak attraction between a negative and a positive. But it's not ionic, because look at this molecule. See how it's bent? And there's positive here and negative here. What type of bonds do you think are in this one? Polar. And what type of bonds do you think are in this one? Polar. So we have a positive end of one molecule and a negative end of another being attracted to each other. Now with me? So that's what a hydrogen bond is. It's an attraction. Oh goodness. An attraction between polar or ionic molecules through hydrogen. That's an 8. I'm about to write. Oh, goodness. It's not going. That's hydrogen. Okay, through hydrogen. An attraction between polar or ionic molecules through hydrogen. So notice this hydrogen here is attracted to this nitrogen here. It's not just between atoms, it's between whole molecules. Does that make sense? Can I erase this? So now here's what I need you to do. I need you to read the descriptions and draw lines to connect the description to the correct bond. All right, so covalent, where did we draw a line to? Straight across. And polar covalent. What? Third one? Here? Okay. What about ionic? The last one? And hydrogen? Second one. Which one of these do you think is going to be the strongest one? Okay, why? You're right. Because they're equally and they're shared, right? There's no transferring or anything else. They're actually both hanging on equally. So this is our strongest. And we see this a lot between carbons and hydrogens. Lots of covalent bonds. Which one do you think is the weakest? The hydrogen bonds are the weakest. We see these between water. We also see them in DNA. So that's your basic chemistry lesson for today. Y'all okay? Ready to learn about water? Yeah? All right. So water has several properties. But first you need to know what it's made up of. I can remember when my kids were little, we left notes for them to get some stuff done while we were at school. They had a babysitter, and they had to make water bottles to take to soccer with them because we were gonna like show up, pick them up, bring them, and I wrote make H2O bottles. And I got home and I was like, "Where's your water bottles?" They're like, "What do you mean?" I was like, "You didn't make water bottles? You didn't get your water ready for soccer? You didn't tell us to do that." I was like, "Yes, I did. H2O." And they were, "We didn't know what that was." Now they were really little, but at the same time, they had no clue. They were like, "We didn't know what you were talking about, Mom." So 1 oxygen, 2 hydrogens, H2O. We know that formula, right? Please say yes. They're all held together by polar covalent bonds, meaning they're not shared equally. The electrons are closer to oxygen, which gives it a bent shape. So it looks like a Mickey Mouse head. Y'all see Mickey Mouse? So when you think water, you need to think Mickey Mouse. So if they're not shared equally, and the electrons are closer to oxygen, what could you tell me about water? Well, okay, maybe it's not very strong, but maybe it forms not very strong hydrogen bonds, right? But how can it do that? What do we know about this end over here by the hydrogens? There would be what we call partially positive, and down here would be negative. So now I want you to draw a picture of a water molecule. Why? Because I need you to get practice drawing this. But don't use the whole page. Or the whole square. Just draw one in part of it. Label your oxygens. Label your hydrogen. Give it charges. Then I want you to draw another one. Wherever you draw it. You don't always have to draw it looking like Mickey Mouse. You can draw it upside down, however you want to do it, and then draw another one. Now, what did we say about opposites? They attract. So what could you tell me about this water molecule and that water molecule? Would parts of them attract? Would this oxygen be attracted to this oxygen? No. What would be attracted in this molecule to this one over here? The hydrogen to the oxygen. What type of bond is going to form? What?
Hydrogen.
Say it.
Hydrogen.
Hydrogen. That weak attraction, we see hydrogen bonds form. What about this one and that one? What are going to be attracted? The oxygen and the hydrogen. If I were to draw another one over here, could these be attracted? Could this be attracted? What am I starting to form? A bunch of bonds that kind of looks like it could be like a net, right? Y'all see that? One molecule is kind of attached to another one? Okay. So keep that in mind when we start talking about these properties of water. These hydrogen bonds are very, very important. We call water a polar molecule. Why do we call it a polar molecule? What? Because they're unequally shared electrons, yes. Has a polar covalent bond, it is a polar molecule. Y'all with me so far? All right. That should say, what does it mean to call a molecule polar? Can y'all see that? Did I write it in for y'all? Okay. Means there's a positive end and a negative end. It means the electrons are unequally shared. And it means that it can form hydrogen bonds. Water is the most common polar molecule that we're going to talk about, but there are lots of other molecules that are polar. Most polar molecules will dissolve in water. Why? Because we can have negatives and positives attracted to each other, and they can start to spread apart. And this is just kind of going through the stuff we've already talked about, showing you pictures. But it is polar because there's an unequal sharing. Oxygen's greedy. The real term for that is electronegative. In case you see that somewhere. So the first property of water is that it's a polar molecule. We're going to be going through the properties. The first one is that it's polar. Okay? The second one is that it can form hydrogen bonds, which we just talked about, right? Those hydrogen bonds form between one molecule and another, a hydrogen and an oxygen. It's a weak attraction. It's easily broken. Right now, why don't you go ahead and, nope, something. Are y'all good not drawing them again, since we just drew them? This will be good practice for you when you're studying. I want you to take your cup and fill it up to the brim with water. But before you touch the plastic cup, I want you to put your gloves on. That's how we're going to kind of keep from spreading anything. I'm also going to ask that you don't touch anything on the table, on the tray until I tell you to, but you also only touch what you need to use. Don't rub everything, okay? So put your gloves on, get a plastic cup, fill it with water to the brim, and don't spill it on the Chromebook. Can you get the cup to work? You trying to figure out where the water is? Yeah, you use it in the sink. It's gonna come out real fast, so turn it on first before you stick the cup underneath it. What? Oh, that's not good. All right, just use this. Fill it up to the brim, best you can. Oh, that's because the water hasn't run through hot water. So there's dirt in them. If you want to dump it and get a new cup, you can. Like, not a new glass of water. You can. See, this is how I learned how messy lab is going to be for me. Usually it's the guys who are messy. Apparently that's not the case this time. All right, so when you get that cup, I want you to look at the surface of it.
Yes.
Can you see the water molecules?
I didn't know.
What?
I can barely see anything.
Okay. Can you see water molecules in it?
No.
No. Because they're smaller than microscopic. We can't see them. But they're there. And if they're there, is one water molecule attached to another? Yes. Through what type of bond? A hydrogen bond. Those bonds are so strong, it's what causes you to belly flop. Anybody ever belly flop? So your whole body hitting that water doesn't break the hydrogen bond. That's why it hurts so bad. But how many of you have a favorite superhero? Favorite superhero? I do. But it's the original Superman. Like the one y'all probably never even seen before. Christopher Reeve Superman. He's my favorite superhero, alright? But you all have your own favorite superhero, but today I'm going to get new favorite superheroes. Everybody take your finger. Stick it in the cup. You're so strong, you broke bonds with a single finger.
Whoa.
So you have a superpower. Go home and tell your parents. Your whole body can't break them, but your finger can. All right, so that's just for fun. Keep your cups of water there. Let's keep moving. You need me? So your job right now, before we move on, we talk about two properties of water. It's polar, and it can form hydrogen bonds. Now I want you to read this. It says to underline the claim in green, but let's underline the claim. Let's put checked by the evidence, and let's circle the reasoning. So you read it, underline the claim, put a check by the evidence, and circle the reasoning. That's what you're doing right now. You should have it on the next slide. Am I correct? Did I copy it for you? Okay. All right, so Colin, read me what you marked as the claim. Covalent bonds are stronger than hydrogen bonds. Do y'all agree? Eva, tell me something you marked as evidence. Okay, good. Another piece of evidence, Brian.
The electricity of water requires a minimum of 237,000 J of electrical energy to disassociate the atoms of each one.
Okay, good. What that means is it takes a whole lot of energy to separate two water molecules. You need me?
I'm sorry, I just walked in and said hi as you were talking.
That's okay, hi. Anybody else have any other evidence? All right, Kate, read me part of your reasoning.
Melting water involves breaking hydrogen bonds between molecules while disassociating atoms involves breaking covalent bonds within molecules.
Okay, good. Is there other reasoning? Does this last sentence fall under reasoning as well?
Yes.
Yes? Does the reasoning link the evidence to the statement? Okay. And I know it's real chemistry termish, but I just wanted you to practice your claimed evidence reasoning. Okay with that? All right. So let's move on. Next property of water. Water is less dense as a solid than as a liquid. Water is less dense as a solid than as a liquid. If something is more dense than water, what does it do? It sinks. Does ice sink? No. Ice floats. Why? Because when we freeze water, all of those hydrogen bonds cause the water to spread out more, and when it does, it becomes less dense, so it floats. It's one of the few molecules that in a solid form is less dense than in a liquid form. So if you look at these pictures, this is showing you water or ice in solid form. Look how spread out the molecules are, but then look at it in a liquid. Are there more molecules in a certain area than there are here? Because density would say in this area right here, and in this area right here, which one's going to have more molecules? The liquid one will, because they can get closer together, but as they freeze, they become crystal-like and more spread apart, so it causes them to float. It does provide insulation for organisms when the ice floats. So imagine if it gets really, really, really cold, and the top of a lake freezes, and then it sank because it was more dense. Would that cause problems? What's it going to do? Okay, it's going to crush everything underneath it. Is it also going to change the temperature of the water below it? So then we have a layer freeze and it sinks and it gets colder, and a layer freezes and it sinks and it gets colder. If those fish didn't get crushed, are they going to freeze to death? Yes. So instead, when that water freezes on top and it floats, it's providing a safe environment for all organisms underneath, but it's also keeping that really cold temperature from the environment from reaching the water below it. Now that water is still cold. Don't think I'll drill a hole in the ice and jump in and I can go swimming. It is still cold. It's just not as cold as it could be. It's not cold enough to freeze. Does that make sense to you? Questions? No? Okay, here's a fun fact. When you watch a sitcom and they're all sitting at a table and they have drinks, look and see if their ice is floating. That sounds silly, but I'm a science nerd, right? And so this is like one of those things, like I would look at my husband and go, that ice is not floating, it's fake. And he would get so wet. He's like, what? Well, they've gotten better and they've started using plastic ice. They don't use real ice because it creates condensation and makes for a messy table. So they use plastic ice that floats now. But it used to be that they use these solid crystal-like pieces of like plexiglass, but in the cube form, and they put them in the water, and they were more dense than the water, so they sank. And so you could look at the cup, and all the ice is sitting at the bottom, and I would just get infuriated. They would ruin the whole show for me. So if you watch older shows, like Boy Meets World, it happens in that. Y'all ever watch that show? Or Friends, or Three's Company, I don't know. There's a whole lot of older shows where the ice sinks. They've gotten better about it, probably because of people like me. But this is fun fact for you. So that's your third property of water. One more. Fourth property of water. Nope. Let's do another CER. Let's not. Let's skip the CER right now. Y'all okay skipping it? Okay.
Yeah.
I want to play with water. Let's see how well y'all do. Third one. Water can absorb a lot of heat. Different liquids have different characteristics. If I put water on the table and I put alcohol on the table, which one's going to evaporate first? Water. I mean, not water, alcohol. Don't believe me? In that little container is alcohol. If one of you will very carefully just pop the lid off and set it next to it. Don't. Now remember, we're touching things as little as possible, so once you pop the lid off, just put it back on your tray. We're not going to put the lid back on it. Each of you needs to get 2 pipettes. It's okay. And open one of those pipettes, dip in the alcohol, and take a drop of alcohol and kind of drag it out on the table. Just take like 1 drop and just kind of drag it out. We have a little alcohol streak on the table. Then you're going to do the same thing with water. And then you're just going to let them be. But put your alcohol pipette by the alcohol streak, because you're going to need it again later. Put your water pipette by the water streak. Is it hard to open those with the gloves on? I'm sorry. Look, those gloves are going to allow us to do more labs, so we're just going to have to accept them as a necessary evil. So just make sure you know which pipette was your water, which pipette was your alcohol. Set them by the streets. We're just going to let them be, and we're going to see which one dries up first. Hopefully one will dry up by the end of class. But what it means by a high specific heat, it means it has to absorb a whole lot of heat before it changes temperature. This is why when you have how many of you have a pool or access to a pool? If you go swimming in March, even if it's been hot and sunny since the end of February, you go at the end of March, is your water real warm? No. It gets a little bit warmer by the end of April. By May, it's maybe tolerable, right? But it takes a long time for it to warm up. Why? Because water has to absorb so much energy before it can actually warm up. Whereas if you had a pool full of alcohol and you were to jump in at the end of March and it's been sunny since since the end of February, you probably wouldn't have much left in there. It would have evaporated because it takes very little heat to make it evaporate. Okay? Usually I would have you blow on these streaks and they would evaporate much quicker, but we can't do that. We can't do that, Nick. So we're just gonna watch it. I know, isn't it? There's gonna be more fun. But it takes a lot of heat to warm water up. So our body is mostly composed of what? Water. So when we walk outside and it's 110 degrees, why is it good that it takes a lot of energy to warm water up? So we don't evaporate, right? Or why, in reverse, water also has to lose a lot of energy to get colder. So when you walk outside, and we're having one of those days where it's 6 degrees, like one of those days that we have like every 5 years, right? And it's 6 degrees outside, and we walk outside, Why is it good that it takes water, why is it good that water has to lose a lot of energy before it freezes? So you don't walk outside and like, I'm done, right? It's frozen. We don't want that. So it helps protect body temperatures. Water is part of the reason why I can take your temperature and you're within 0.1 degrees of what you were 2 days before. Because water allows our body temperature to be regulated. If we had a body that was mostly made out of alcohol, it would not be good. We would walk outside on a hot day and we would be no more. Questions on high specific heat or it has to absorb a lot of energy? So this is just talking about how we can use water and sweat to allow us to cool off. Y'all know that's why you sweat? Okay. So when you sweat, why do you do it? Okay, because your body temperature is getting hotter, so you start to sweat. How does sweat cool you off?
The water absorbs the heat.
Because the water, as it gets on your skin, starts to absorb the heat from your skin. When it absorbs enough of that heat, what does it do? Evaporates. Anybody ever notice when you're really, really sweaty, and then maybe a wind comes, or you sit for a little while, and then all that sweat starts to dry and evaporate off of you, and you start to feel what? Cold, right? Because it's absorbing the heat from your body so that it can evaporate. It's called evaporative cooling. Now, you said there was salt on your skin, right? You're absolutely right. That salt causes the evaporation point of water to decrease, so it doesn't have to absorb as much energy before it evaporates. So it has to absorb a lot, but not as much. That's the purpose of the salt. That, and it also is a natural kind of antiseptic for your skin. But that's why we sweat. We sweat so that it evaporates and your temperature cools, because it's literally pulling the heat away from your body. Does anybody know how dogs sweat? Their tongue, right? So the hotter they get, the longer their tongue seems, right? All right, so now you're going to take a drop of alcohol, we're going to put it on your arm, and a drop of, use this part of your arm, it's more sensitive. Just one little drop of alcohol, one little drop of water. If you're, for whatever reason, if alcohol irritates your skin, don't do that. One drop of alcohol, little bitty drop, and a little bitty drop of water. Pay attention to which one's where. Kind of go like this once you get them on there.
I did maybe a 4 or 3 drops.
You do a few drops? That's okay. You'll be fine. What drop is starting to feel cooler faster? The alcohol should be, because it can absorb a lot more heat. Which one do you think is going to dry off faster? The alcohol. So if somebody's really overheated, what could you do?
Pour them the wall.
Not necessarily cover them in alcohol, but could you take a paper towel with some alcohol and like rub it on their forehead? Absolutely, it's gonna help cool them faster. Alcohol has a much lower specific heat, so it takes a lot less heat for it to evaporate off of you. Alcohol won't ruin your clothes or anything else, I promise, so you're all good. All right, so I gave you a CER. We are going to do this one real quick. I want you to correct it. What would make it better? What does that mean? Are you asking me something? Okay. Okay.
Oh, I thought we-
What is just one thing you would have fixed about it, Tanner?
He didn't specify what degree of, temperature he's using.
Okay, so give units? Is that what you're saying?
Yes.
Okay, so maybe put units. What is the claim in this one?
He is number one.
It is number one. What could we have said instead to make that better?
Liquid number one is no science performance.
Yeah, so we could say liquid number one. Y'all see this right here? It's ambiguous. Don't ever use it when you're writing a conclusion. Instead of using it, write the word you want it to be. Because it, a lot of times when you write a conclusion, could refer to a whole lot of things. I want the stamp with the it clown. When we use it, I can just stamp it on top of it. What are you talking about? Scary clown? I don't know. Right? So don't use it. Then our evidence, it says liquid one has a freezing point of 32 degrees Celsius. Do you agree with that statement? What is the freezing point of water?
30 degrees Celsius, 32 degrees Fahrenheit.
32 degrees Fahrenheit, it's 0 degrees Celsius. So, would liquid number one necessarily be the right one? What would be the right one?
Liquid number two.
Maybe liquid number two. So we could say liquid one has a freezing, or liquid two has a freezing point of 0 degrees Celsius. Is there any other evidence we could use? Yes, we could say liquid two has a boiling point of 100 degrees Celsius. Does anybody know what the boiling point of water is in Fahrenheit? 212. So now our reasoning, water has a freezing point of 0 degrees Celsius, which matches the freezing point of liquid number two, right? And could we also say that water has a boiling point of 100 degrees Celsius, which matches the boiling point of liquid number two? Feel like you're getting better at CERs? Yeah? You already hating CERs? Yeah, you know what? I don't like to grade CERs. They take a long time. So we're going to get really good at them, and then won't do as many of them. We'll just practice them periodically. Is that okay with y'all?
Why would you get good at something if you're not going to do it?
No, we're going to do it. We're just not going to do it 3 times in one day. So I'm going to make you really sick of them, and then I'm going to kind of ease off a little bit. Come on. All right, the fifth property of water. Water molecules are cohesive. Water molecules are cohesive. Anybody ever had to have something, if you had to put an ice bag on it and a trainer or a physical therapist or even at a doctor's office, they'll put this tape on you. They call it pre-wrap, and they'll wrap it around your skin, but it doesn't stick to your skin. What does it stick to? It sticks to itself. It's called cohesive tape. All right, it is designed to stick to itself. So water molecules are cohesive. That means it sticks to itself. One water molecule sticks to another. What causes one water molecule to stick to another? You've already drawn them once. Hydrogen bonds. And what property of water allows it to form hydrogen bonds? Because it's a polar molecule. It has polar bonds, so it can form hydrogen bonds, but the hydrogen bonds allow it to stick to itself. This is what creates what we call surface tension. You ever seen a bug walking on water? It's not strong enough to break the hydrogen bond, so it can walk on water. All right? So surface tension is also what causes you to belly flop. Because those hydrogen bonds make like a solid surface. So right now, I want you to get your cup of water, and I want you to get a paper clip. And first I want to tell you, a paper clip is more dense than water. So what should that tell you? It's going to sink. I want you to make it sit on top of the water without touching the side of the cup. It's possible.
Without it touching the front of the cup?
Yeah, it's just going to be on the top of the water.
Oh, my.
It might be really hard with the gloves.
It don't matter.
So then you can get it out. If you need to use the sink, use the sink. I'm giving you exactly 4 minutes to see if you can get it done. We've got 2. This one, you only get 1 paper. Just don't water.
It's gonna spill around. It's so big.
All right, we got 3. How many of you are so impressed with yourself if you got it on there? I'm really impressed that y'all did it with gloves, because that makes it a whole lot more difficult.
Is it possible to get out? How'd you do that?
How do you make it funny,
Your alcohol's on?
I gotta lay there.
No, I can't hear. Right there. Guys, has all the alcohol evaporated? What about your water? Alcohol has a much lower specific heat.
No, it's not. Yeah, no, I can't
This
get
is
one.
all international engagement.
So we might have.
All right, guys. Got about 30 seconds to try and get it to float, but not really close.
I did it, but it fell.
So if you weren't able to do it, go home tonight and see if you can do it. Have a competition with your family, see who can do it first. Teach them what you learned in class.
That's all.
What?
That's all.
Yes.
Oh my God.
All right. So,
No.
no. Go home tonight, challenge your family to a paperclip floating competition and see who wins. All right? But paperclips are more dense, so they sink. So if they sink, are they really floating? No. Why can a paperclip sit on top of water?
Because it's for the area of the paperclip. If you expand the surface area, it is
Okay.
Something about the amount of displaces is the useless.
Okay. So why can this bug walk on water?
It's small.
It's small, and what is it not doing? What creates surface tension, that solid surface in water? Hydrogen bonds. What is this bug not doing?
Breaking the bond.
Breaking the hydrogen bonds. It's not breaking the surface tension. So when a paperclip sits on top of water, it's literally sitting on top of water. It's not floating. Floating is not sitting on top of water.
Just like how we do it.
That would be floating, because you're breaking the surface. But that paperclip is literally sitting on top of those hydrogen bonds. It is not floating, it's on top of the water.
So are we floating on air? We're breaking the surface of air, so. Oh.
No, we're not floating on it, but we are surrounded by it. But the paperclip is sitting on top of the surface tension because surface tension creates a solid surface. It's a liquid, but we create a solid surface with it. So that paperclip is sitting on top. Does that make sense? All right. So if you need to get a paper towel and kind of wipe a few things up, you can get the paperclip out if it's at the bottom in a minute. Y'all didn't get any paper towels? Forward. Property number 6. Property number 6, water is adhesive. What does adhesive mean? It sticks to something. Anybody ever use adhesive tape?
Yeah.
Scotch tape, duct tape, masking tape. How many of you use adhesive tape to stick tape to tape? You get one piece of tape and you get another piece of tape and you stick it together and you're like, this is what tape is for. All right. They put the solution on both sides. But is that why we get tape?
No.
We get tape to tape two things together. Maybe you're going to hang something on the wall. You're going to make the paper stick to the wall. Right? So adhesion in water means that water sticks to other things. Okay? So anybody ever seen a leaf in the morning when there's a bunch of dew and the leaf's kind of hanging, there's this droplet like hanging from it, and gravity says that droplet should what? Fall, but it doesn't. Why? Because water is sticky and it sticks to it. Water will stick to other substances that are polar. So glass has a polar quality to it. So when you get in your car in the morning, you see the droplets of water. Gravity says that that water should drop down the windshield, but it doesn't. It sits there. Why? Because it's adhesive. It's sticking to it. Does that make sense? So cohesion means it sticks to itself. Adhesion means it sticks to
things that are not itself.
other things. Yes. So it sticks to other things. Capillary action. Anybody ever had to have their blood drawn at, not like your finger prick at the doctor's office? Right, you get your finger prick and then they get that bubble of water or a bubble of blood, and what do? They stick a tube on it, and when they stick the tube on it, which way does the blood go? Up. Guess what one of blood's main components is? Water. So as it goes up that tube, those molecules are sticking to each other. So as one goes up, is there another one stuck to it? It pulls one. So as it goes up, it keeps pulling another one with it, right? But it doesn't fall back down because water is also sticky or adhesive, and it's sticking to the inside of the glass. Does that make sense? So that's what pulls it up. It's called capillary action. That's also how your blood can move up your legs more efficiently. Because it's water pulls one, and it sticks to the inside of it. Now, how is that important in living things other than humans? How could capillary action be important? We're not talking humans, or let's not even talk animals, because y'all could say, well, the blood's coming up the dog's leg. Yes, but how is it really, really important? Yes.
So that your legs don't die.
Okay, but not in animals.
So that animals' legs don't die.
No, we're talking about not in animals. So another reason it would be important. Like, forget about animals. In living organisms other than animals, yes.
Oh, living organisms?
Yes.
Oh,
Like in a plant, or
Okay, but not the nutrients necessarily,
The
but
water.
the water. Absolutely. Have you ever seen the pictures of big redwoods? They're like super, super tall, right? Where does the water that they need for the top of the tree come from? The roots. So it has to defy gravity and go up. How does it do that? Through capillary action. Through cohesion and adhesion. So plants, it becomes very important. So there's those giant trees. The water's got to go from the bottom to the top against gravity. It does that because water molecules are cohesive and adhesive. And let's just explain. Did I give you this one printed out? No? Okay. So plants, it's cohesion and adhesion. It's called that capillary action. It's really important. It's a very important property of water. All right. Let's see. All right. We're going to do this in just a second, but let's talk about the last product, the last property of water. It's a universal solvent. What does it mean to be a solvent?
It's all dissolved.
It dissolves. If it dissolves things, the solvent does the dissolving. What is the stuff that is being dissolved called? Anybody know? The solvent dissolves. The solute. What is dissolved? So name something you can dissolve in water. Sugar.
Spice.
What?
Spice.
Spices. Okay, some spices, yes. Salt. When you think of cooking, most of the things that you're going to dissolve, you're dissolving them in some water-based substance. Because water is a universal solvent. Does it dissolve everything? No. But it dissolves a lot of things. And that's good for our body, because when we get nutrients and they dissolve in water, does that make it easier to get where it needs to go in your body? Absolutely. But the solvent is what does the dissolving. Solute is what is dissolved. So if I take this water molecule, remember this with the hydrogen bonds, and I add salt. Salt is ionic. So it's Na plus Cl negative. Because remember, electron is transferred. So we have a positive atom and a negative atom. They're attracted to each other. Well, if I drop those in here, where's the sodium going to be attracted to? The oxygen, because it has a negative charge, right? And where's the chlorine going to be attracted to? The hydrogens, because they're positively charged and opposites attract. So now I've taken the salt molecule and I've broken it apart or disassociated it, and it's dissolved. That's what happens with sugar. It breaks apart and it's dissolved because parts of it are attracted to either end, and that's what causes it to dissolve. Does that make sense? So water is polar. It forms hydrogen bonds. It has a high specific heat. It is cohesive. It is adhesive. What one did I forget? I forgot one.
Soluble.
Yeah, it's just cohesive. The solvent,
Soluble.
yeah, the universal solvent. That's soluble. There's one other one that I've forgotten to mention at the moment. So there's your 7 properties of water. All right, universal solvent is the last. So what we're going to do now. Let's talk about these terms real quick. Hydrophilic. What do you think hydro means? Water. Does anybody know what philic means? Loving. So hydrophilic means it's water loving. These are molecules that will dissolve in water. Hydrophilic molecules are polar. or usually polar, or they're ionic. Meaning they have ionic bonds. What do you think a hydrophobic molecule would be?
Because it's water hating.
Water hating or water fearing, right? If you have a phobia, you're afraid of something. So hydrophilic is water loving, polar or ionic. So if it's water loving, do you think it will dissolve in water? I mean, if it's water loving, it just easily goes into water, right? So hydrophilic molecules will usually dissolve. So we said sugar dissolves in water. Do you think sugar is hydrophilic? It is. What about salt? Yes. So then we have hydrophobic molecules. What does this mean? Water fearing. Do you think polar molecules are going to be water fearing? No. So we call them non-polar. These are just the ones with covalent bonds. I can't write. So they don't have polar bonds, they don't have ionic bonds, so they're non-polar. Do they dissolve? No. So think of something you can add to water. Yes. Oil. Anybody ever added oil to water? Oil, if you pour oil in water, do they even like mix it all? No, they separate. Alcohol and water. If you put alcohol and water together, you can shake it up and let it sit for a while, and alcohol is going to separate from water. Because it's hydrophobic. Everybody with me so far? Okay. So we're going to go back to Go back to the slide that talks about the pennies. Here's what you're going to do. You're going to get 2 pennies, 2 pipettes. You have a beaker of water. You have a thing of alcohol. Put your pennies on a paper towel because it makes it a lot less messy. One penny, you're going to put as many drops of water as you can before it spills over. So if I'm at like drop number 122, and then when I put 123, it spills over, how many could it hold? 122, that's what I'm going to record. I'm going to do it twice for penny and twice for alcohol. And I'm going to record both on the day-to-day. Y'all have the day-to-day one, right? Okay. So you're going to do that and work quickly. Do one for water, one for alcohol, then go back and do a second trial for both. That way you at least have one of each.